Okay, awesome. All right, so welcome to the second lecture of the course. So we discussed about stable curves, realizing stable curves in terms of the components of their normalization. So we had this statement that if I have a curve C, something like that, if I look at the normalization of this curve, we call it C tilde. C doesn't need to be irreducible, it could be a reducible curve. So we had this condition that you look at irreducible components of C tilde. So these are some varieties of C tilde, and depending on what their genus is, irreducible components, then we need to see whether they are stable or not. So we had that if this thing is genus 0, we need to have at least 3 special points. Special points really mean pre-image of nodes, which we called QIs in our notation, and marked points, which we called PI in our notation. So 3 of these things total. If C is an irreducible component of the normalization and it has genus 1, we need to have at least 1 marked point, 1 special point. Or for other components, C, if C tilde irreducible is genus bigger than 2 and higher, no condition is needed. Condition is needed because it is in fact proven that algebraic curve of genus bigger than or equal to 2 has finite automorphism. Okay. And this is what we did. So an example of this thing is, as I said, I can draw things in real dimensions. So this is an example of genus 1 curve. It's like a torus, and then it would be connected to some component which has genus 2, and it could have some irreducible component which meets it at 2 points like this. Okay. And this is genus 0. So this is genus 1, this is genus 2, and this is genus 0. Okay. So in this picture, you are looking at nodes. So these are the nodes. These are the nodes. Q1. Oh, okay, so I can call the node something else. I can call it x1, x2, x3. And then I can look at normalization of this thing. So normalization, normal variety. So it kind of separates these pieces. So it looks like this. And this has 2 nodes. You see, over here. And then there is this guy, which has 1, I mean, this is the pre-image of the nodes, basically. These are smooth components. And then you have this piece in here, which is the P1 component, which has 2 nodes. So this is what the C tilde looks like. And this is irreducible component of C tilde, irreducible component 1, C tilde irreducible component 2, C tilde irreducible component 3. So is this picture stable or unstable? You look at the components of the normalization. The genus 1 part has a special point, so this is okay, because a special point could be pre-image of a node or pre-image of a marked point. The genus 2 part doesn't need any condition, because this thing has finite automorphism group also, naturally. This one is a genus 0 component and needs to have at least 3 special points, but it doesn't. You can see the pre-image of the 2 nodes. Okay, so this is also here. preimage of the two nodes, but you cannot see anything else. So this thing is unstable. So this thing is unstable, which implies that this original singular curve is also unstable. Okay, so this is much easier to read off rather than writing equations for these things and calculating the order of an automorphism group of the ocean. In order to make it stable, remedy to make it stable, we can change the geometry or we can add a marked point. So add a marked point. That will fix it. Why is adding a marked point changing the automorphism group? Because it's not just labeling some, it's not like we are taking a marker and putting a point on that thing and labeling it. It's not like that. We are restricting the possibilities for maps that can take this configuration of curves to itself, because when you add a mark point, the restriction is coming from the fact that you need to have that map fixing the mark. So as soon as you add a mark point in here, you're looking at a much smaller set of possible maps. So if I have a marking in here, marked point, and I call it P1, then this thing will have a preimage in here, preimage of P1, so P prime 1. And basically, that's making it stable. So add a mark point. So then we can say that C together with the mark point P1 is stable. Because now if I look at the genus 0 component of the normalization of C, it has 2 points, 2 preimages of the two nodes, together with preimage of the marking, and that fixes the infinitely many maps that can be sent it back to itself. Okay, so this is that example. Okay, so we have discussed about automorphisms and the stability of the connected curves, because we are interested in the spaces that parameterize these algebraic curves up to automorphisms, and we don't want this space to, we don't want these things to have group of automorphisms given by infinite order. So we don't want that. So we are hoping that the space that parameterizes these algebraic curves is going to be a moduli space and a Deligne-Mumford moduli stack. That's what we are hoping. Not that we are not able to deal with Artan stacks. To some extent, sometimes we can. And we will discuss that too. All right? So that's that. Okay, so that's the example. Now here's a definition. Definition given G and N bigger than or equal to 0 to integers, and N pointed family of smooth or stable applies to both genus G curves over a scheme S is a tuple as follows. It's a map from total the space of this family. I'm going to call it C to S, together with markings P1 to Pn and mark points which are maps from S to C. So it's a tuple like that, where I is a smooth or flat. So it could be a parameterization of a smooth curves, in which case pi would be smooth. It could be a parameterization of a stable curves, in which case it would be at least flat. Flat really means that fiber-wise dimension of fibers of pi, for instance, do not jump. Okay, proper projective, finitely presented, morphism of schemes such that the fiber C, let's call it S, over any geometric point, S little s in is parameterizing the scheme. S is a smooth or stable, depending on what family we are considering. It could be smooth, it could be stable. Okay. Smooth or stable, projective, connected curve of arithmetic genus G. Okay, so if you want to consider families of curves, you pick some underlying parameterizing the space. We are doing algebraic geometry. A notion of a space alone doesn't help us. We would like to think of a space as a scheme. So we would like to have this space having the locally be constructed as a, in some sense, geometric realization of a sheaf of rings. So we would like to be able to have a ring of polynomial functions. Locally, we can cover this space with open patches, where those open patches locally have the algebra of the polynomial rings, commutative. So we want that thing, exactly how Grothendieck constructed these schemes. And so that's the underlying scheme. And then we would like to have the family to have fibers over the underlying scheme. Each time I pick a point in here, this is the total space of that family. Each time, fiber of this thing needs to spit out for me one of those curves that we are parameterizing. And we would like the fibers to keep being flat at least, meaning they don't jump in dimension and things like that. Okay. All right. So the morphisms, so you see, mark points are points. But now, because I'm discussing about the family, I want the mark points to be morphisms from underlying a scheme S to the whole family. So the morphisms, now they are morphisms. The morphisms P1 to Pn are pairwise disjoint sections of pi from C to S. So these are sections of this morphism. This is what the PIs are. Okay. And okay, with image, the smooth locus of pi. Okay, so you kind of want, so fiber-wise, P1 to Pn are going to be the mark points on the fibers. But think about it. You have a curve. think about one curve. Okay, so maybe I can actually draw this picture for you. So let's say I have a curve. This is one of those curves. Let's call it C. Okay, it's a smooth curve, but this curve can also become singular, which is fine. Stability doesn't tell us you're not allowed to study singular curves. We just saw a singular curve. We had normal crossing singularities and so on. So you could have smooth curves, or you could have singular curves. Or you could have normal crossing curves like this. Okay. And then you would like to remember, in order to fix the automorphism group of this thing, you would like to remember certain locations on this. These are those things that we are, again, discussed that we are interested in that because we know under infinitesimal deformation, the curve, the surface represented by this algebraic curve develops some kind of singularity. So we kind of do that. So we put some markings in here, let's say, and in here. Now the mark points need to have the property that they need to be on the smooth part of the curve. These are smooth mark points, okay? So we can have nodes, which doesn't need to be a smooth locus. Obviously it's not, but the markings need to be smooth, on the smooth part of the curve. So, okay, I can put marking in here, P1, P2, Pn. And for the rest of these curves too, so I can have P1, P2, Pn. P1, P2, Pn. Okay. So I'm looking for a family of these things, a family which parameterizes all pictures like this and also parameterizes all of these mark points located at the smooth locus of the curve. So there must be a family that gives us that. And so that family is over some underlying parameterizing the scheme. So we are going to call this parameterizing scheme scheme S, S standing for scheme. And we would like to think that this family is total space of fibers like this, which for a point of the scheme, let's say S0, I can see pictures like this. Then for some point, I can see some other picture like that, and it keeps going. So SM, whatever. Okay, so that's what it is. And then, okay, so far you can see the picture, but then if I look at the total space of this family, this is what I'm going to call big C, and this map pi now is the one that we have in here. And then you can actually see, as you look at all of the possible fibers, the mark points become sections of this vibration. So I just need to keep track of where the P1 goes to. I just need to keep track of where the P2 goes to. And I just need to keep track of all the way, oops, where the Pn goes to. So as you look at this in families, you can see that this section is a map from S to total space. This section, think about a vector bundle together with a section of it. So P1 is a section, and this in realization over the family, P1 becomes a section, and P2 becomes a section, and P3, Pn becomes a section. So that's why, as you look at these things in families, markings become morphisms, sections of this vibration. Okay, so that's what it is. All right. That's the idea. Okay. So we say that. So now I have families. I have defined a notion of families, but I would like to identify families with each other. Right? Can I identify? So we say to say that a second family let's call it C prime over S pi together with P prime 1 to P prime n from S to C prime is isomorphic to this family. So sometimes I use this notion quotient C over S because I can do it because it's the way I read it, C over S. So pi is giving you a map from C over S. C over S, so I'm writing all the possible notations, basically. Okay? So is isomorphic to this family if there exists an isomorphism. Now everything is a scheme theoretic, so these isomorphisms are morphisms between the schemes. So if there is an isomorphism of the schemes from one family, from total space of one family to the other, such that this isomorphism maps the points, the markings to each other compatibly. So such that phi OPI is the P prime I. So you have this family from pi over S. You have another family, I prime over S, and you have morphism between them, phi. Exactly. So the markings of this family are given by the PIs. So you would like to take morphisms like here by PIs. You look at the morphism over there, and the markings of this family are given by P prime i's. So you would like to take points in here and map them and have them land on P prime I. And this is the thing that guarantees for you that if you have a space that parameterizes these things, you're sure that you will be guaranteed to basically parameterize Riemann surfaces which are pinned at certain points in the space. If you can construct a machine that gives you families with this notion of isomorphism, and that's your moduli functor. Okay, so that's that. Okay, so I delete this picture. All right, given a map, let's call that map F from T to S. Not only I can alter families over the same scheme, I can also alter the base of the parameterization. So let's say S for me is a line. Then the parameterization will be for every point of a line, I have a curve. Every point on that line is a curve, a stable curve, or a smooth curve, whatever. Okay, but then I can have a quadratic curve, right? I can have a degree 2 curve. Okay, that's a one-dimensional object, and I need to be able to say, if I look at every point of that parameterizing my family, can I get a compatible family again or not? So if I have a map like this, we define the pullback of the system C over S together with markings P1 to Pn under F, under this morphism F, to be the family, C of T over T together with P1T to PNT for the fiber product. The fiber product C of t is defined as C over S times T with induced sections. Induced sections Pi and T equal to Pi OF times identity of T. Okay, so what's the picture in here? You have C, your original family, over S, that's pi, and then your PIs are sections of this family. And then you're trying to change parameterization, so you can define isomorphism schemes like that, and then you would like to take this family and pull it back and get the family which is parameterized for every point of the scheme T. And that you will do by looking at the fiber product. So fiber product of these two things is C over S times T, and that is the one that we call C of T. And this is F. Okay, and then you want to feed the markings in here as not from points in S, but from points on T. So you would like to pull back these are morphisms from point of S to here, but you don't like that. You want them to be fed from points in T. So you basically look at PIOF in here, and you get these maps over there. Just pull back your morphism. So this is exactly PI of T, the way I have defined it. Okay. All right. So these are important because that's the whole beauty of work with moduli spaces. The very construction of the moduli space allows you to get any kind of notion of family. So moduli spaces and moduli theory, the way that is written in modern algebraic geometry, is that you always start from a functor. It's a machine that you feed in it your parameterizing scheme, and it gives you a family over that parameterizing scheme. So this machine is a functor. So you feed this functor with one point, it gives you one single curve with given markings on it. You give it with line, it gives you a parameterized family of curves over that line. Every point of the line becomes a curve. You give it with the plane, it gives you two-dimensional family. You give it with a cube, gives you three-dimensional family, so on and so forth. So the moduli functor remembers these things. How change of base underlying parameterizing scheme changes the family. It remembers it. Okay? Mm-hmm. Why? You would like, it's a fibered product because you would like this map over T, remember how is T related to S. It's not just, yeah, it is. You can have another family over T. Ah, sure, of course. But that's not what you're interested in. You're interested in knowing if there is a morphism of schemes between T and S. Is there some family on T which remembers this family over S? You say, indeed there is. One of those many, many possible families is the pullback of family on S via the morphism from T to S. Yeah, there are many other families. Sure. Yeah. Okay, definition. Okay. Let M curly M GM and with a bar, M bar curly M bar GN be the moduli functors. Moduli functors. Moduli functors sending. a scheme S in, so okay, I am trying to use proper language of algebraic geometry. Moduli functors are from a category, right? I mean, functor is always a map morphism between two categories. A functor is something that sends objects in one category to objects in the other category. It also sends morphism between objects in one category to morphisms between objects in the other category. But this is exactly what we want, right? Objects, so you pick a category, and category needs to be the one that parameterizes, gives you the parameterizing schemes. This category should have points in it, lines in it, curves in it, two-dimensional schemes, spaces, three-dimensional spaces, all of them. You can enlarge the category as much as you can by weakening its characteristics. I can say, I'm interested in category of all possible schemes over complex numbers. That's a category. For sure, that's a category. All of the things that you want is in that category. It's a really big ball of objects. Okay. So objects in this category are the families, as you saw. Every time you pick one of those elements in that category, meaning a scheme, you will get a family over that scheme. Good. And we would like this compatibility that if I have two objects in that category, this is an object in that category, and this is an object in that category. But there's a morphism between those things. The functor tells you that, yeah, I can remember that. If you give me a morphism between two objects in that category, I give you a morphism between families you constructed over objects. That's exactly that. That's what the functor does for you. So the category is going to be the category of schemes over complex number. For now, of course, you can define these things over any algebraically closed field, but we work over complex numbers. I mean, in this kind of in this territory. So, scheme over C to the sets. So sets. So if I take M bar MGN, this is now the functor. Okay. This means I am evaluating that functor at one of the objects in the base category. So we're seeing it should give me the set of these things. So a family over S together with markings. Okay. So these are smooth curves over S, okay? Set up these things modulo isomorphisms. So I define my moduli functor in a way that if I have two objects which are isomorphic to each other, now we know what isomorphism is. If I have two families of curves, forget about this pullback. Just think about two families. If I have two families, there is a morphism between them, which is an isomorphism, and it respects the markings of this thing and exactly maps the markings to the other one compatibly. I would like to think of them as one family. I don't want to overdo construction. So this is the moduli space, moduli functor, and it's the image of the moduli functor. This functor, the functor MGN sends you from the category of schemes over complex numbers to category of sets. And the set we are interested in is set of the families of these things modulo isomorphisms. Okay. All right. So that's that. And then what is M bar GN? M bar GN evaluated at an element of the category, which is S, for instance. I would like that to be the set of families of stable curves parameterized by S together with the markings okay? And these are stable curves over S modulo isomorphisms. So I want my modular functor to do that. So if I'm saying M bar Gn, difference between MGN and M bar Gn is the difference between the smoothness versus the stability. And you would ask yourself, why am I caring about the stability? Because as you can see, stable curves are allowed to be singular. So what does again that have to do with the stability? Stability is controlling how singular the curve can be. I'm not interested in really, really highly singular curves. I'm only interested in a little bit singular curves. Stability captures that. So if the curve completely folds on itself, that's not the interesting thing for me. But as long as its singularities are normal crossing singularities, like nodal singularities, I'm allowing that. And I can work with that object. Okay, so stability really is a way of controlling how singular the curve can be. So smooth curves, and with the bar, stable curves. Or mildly singular curves. Okay. Okay, so that's that. Okay, so these two of n-pointed, these two moduli functors of n-pointed families of smooth in the first case and a stable in the second case, a stable genus G curves over S parameterized maps up to isomorphs. Okay. Given a morphism F from a parameterized scheme S T to S, the induced maps if I look at the fiber of this functor over S, you see the moduli functors are nice because I can think of them as spaces, kind of. I can treat them as a space. It's similar to the way I'm looking at a space fibered over something. Moduli functor is also a functor fibered over a category. So I can think of fiber of this functor over a category. So that's fiber. The evaluation of the functor at the point in that category is like a fiber. Okay? So I can look at fiber of this functor over S and fiber of this functor over T. I can look at T and S. I can look at S. Okay. Okay, so this is what it is. M bar are defined by the pullback of the families of curves over S to T. So that's what the fiber, the functor, the moduli functor does. So then I have a theorem. Let G and N be two positive integers or 0 with 2G minus 2, with this condition, 2G minus 2 plus N bigger than, strictly bigger than 0. Then A, there exists a coherent coarse moduli spaces straight MGN and straight M bar GN of curly MGN and curly M bar GN. Okay. Part B, they are normal algebraic varieties, of dimension. Okay, so this is a very highly interesting thing, and you need to, if you don't know what the coarse moduli space is, you need to look at the literature. The moduli functor is a functor between two categories. Okay, that's it. This actually says that associated to this functor, there is a space also. And the space is cooked up in a way that it shows you realization of what this functor does geometrically. So this space is in a way that a point in this space is the fiber of the functor over a point. A line or a curve in this space is the fiber of this functor over a one-dimensional scheme. A two-dimensional locus of this space is the fiber of this functor over a two-dimensional space. Okay? In some sense, it's like the image of the functor is being realized as a geometric space. But that the functor is not the geometric space, right? The functor is just a functor. It's a morphism between two categories. So, okay, the coarse moduli space is underlying this. So that's a theorem. And then these two space algebraic varieties of dimension 3g minus 3 plus n. And there is a natural inclusion, straight MGN inside straight M bar GN. You see, I could have monomorphisms like fully faithful morphisms between two categories, right? I can define subcategories and so on. And then the moduli functor is actually a functor, right? I cannot define a notion of inclusion for functors unless I evaluate the functors at the category. But then the coarse moduli space is the underlying geometric space that you could get after evaluation of your functor. As soon as I discuss about the spaces, then I can discuss about the inclusion of the spaces. So there is a natural inclusion. In the level of the space underlying these functors, there is such thing as a non-empty, open, and dense subvariety. All right, so this kind of makes sense. In the level of the spaces which see the evaluation of this moduli functor at different parameterizing schemes, you can obviously see that one would be included in the other as a dense subvariety. There is a space in which you can see points of this space, interior of this space are smooth curves, and then the exterior of it or the boundary of it captures how singular the curves can be. If you pick the boundary really large, you're allowing singularity to be very, very wild. But that's not what we're doing. We're kind of saying, I'm not interested. I don't want to study those things. I pick the boundary so that on the very boundary, I see curves. Every point of the space is a curve with controlled singularity. On the boundary, I would like to see stable curves. And on the interior, I would like to see smooth curves. So if I take a path from the interior or bulk of this space into the boundary of this space, I will follow that path point by point. And I will see that I can see a demo, a cartoon. I see that the smooth curves deforms and becomes singular, but with allowable singular. So interior is a dense subvariety of the compactification of that open dense subvariety. So one of them is the compactification of the other one. Okay. Part C, the variety straight M bar Gn is irreducible, projective, it's compact, and has quotient singularities. It is singular, but it has quotient singularities. Quotient singularity is like when you have a space and there is a group acting on it, you take every point of that space and you keep track of where the group sends that very point. For every point of the space, you keep track of where the points are being sent under the action. So there is a map from the space to another space, which is quotient of that space by the group action. That map sends every point of the space upstairs to the orbit space downstairs. So that's kind of the singularity type of this one locally. Okay? And then a component boundary of this compactification, which is a compactified coarse moduli space minus its interior, is called the boundary of this compactification, and it's called the boundary of M bar Gn, and is a divisor, Weyl divisor or Way divisor. We will show this later. For M0, and I'm going to show you what the boundary of this compactification looks like. And I'm going to show you that it's a divisor. One complex dimension less. Okay? Part D, and then part E. There is the locus. I'm going to call it M bar Gn O, which is a subvariety of the compactified coarse moduli space of curves C with markings with trivial automorphisms that is, i.e., automorphism group of the system of curves together with its markings is a single element group given identity, given by identity, is an open and a smooth subright. Okay. It is a fine moduli space. Fine moduli space really actually is the meaning of this thing. Fine moduli space means automorphisms are trivial. Not only they are finite, but they are actually, that finite group is the group with one element, and that element is identity. Okay. All right. Fine moduli space for the moduli functor MOGN, which is parameterizing genus G curves with n markings, but with trivial automorphism group of stable curves with trivial auto. Okay, and has a universal family. Okay, and this universal family, so this thing sits inside the compactified coarse moduli space, and it has a universal family. Oh, so maybe you can put this in here. So this thing, M bar Gn, trivial autopart sits inside M bar Gn, and it has a universal family, which I'm going to call C Gn, together with sections pi. All right. What is that? Universal family is constructed over the moduli space. And it is the thing that, again, you can look at the fiber-wise description of it. If I pick a point in this space, fiber of the universal family over that point is a genus G curve with n markings with no automorphisms. If I look at the line in here, this is a space. This is some space. If I pick a point in this space and I look at the fiber of the universal family, what I would see would be some curve, maybe with n markings, P1, Pn, with controlled singularity. If I look at the path in this space, a line or curve in that space, and I look at the fiber of the universal family, here I will see this path, and I will see the picture that you saw. If I pick a two-dimensional locus of the moduli space, I will see a two-dimensional parameterized family. And that's why the universal family is interesting and useful. Okay? Essentially, the moduli functor does that for you, but the moduli functor is a functor. So the moduli functor, better to have an underlying space, which is the coarse moduli space, and then that underlying space has the universal family. So we work with the universal families. Okay, so that's that. Okay, so what is it I want to show you? Let's see. Yeah, so maybe I can draw a picture of all of these statements of this large theorem. Well, about families of stable curves. So here is the open dense locus that parameterizes curves, smooth curves of genus G with n mark points. And then the compactification sees kind of, it gives you a boundary for these things. Yes. So let's say a point. So I like to basically show you what kind of bad situations, bad scenario can happen. So if I pick some point in here, in the interior, and I look at it, maybe I can see, okay, maybe if genus is 1, for instance, I can see some situation like this. So I can see n markings on a curve like that. And then I can pick something in this boundary of my moduli space. And that's basically allowing this thing, if I move from here to this boundary on a path, that's basically the realization of deformation of this thing into something with singularities, but with controlled singularities, finite automorphism. So maybe I can take this thing and I shrink it and shrink it and shrink it and make it into a node. So maybe over here I can see again a genus 1 thing, but with a node. So a node here. So I can have P1 to Pn, but now I have this node. Okay. And then maybe on this side of it, if I take this thing and move to this side of it, I can see pictures like how this thing breaks into pieces. All right. So for instance, I can look at a curve like that. Well, depends on, okay, so this is where we need an ambient space. I'm not yet looking at its curves embedded inside ambience, but let's just think that it is. So let's say I describe this curve with a polynomial. It's a curve, algebraic curve. It's a polynomial in homogeneous variables, right? So let's say curve in 2-dimensional space. As soon as I write down an equation in ambient 2-dimensional space, that cuts the dimension by 1 and gives me a curve. So I say it's a curve and I pick a polynomial f1, homogeneous polynomial f1 in that space. Then I can deform this thing and, okay, whatever. I mean, let's say degree 3 polynomial. Okay, then I can put it in a family. This is a degree 3 polynomial, this is a degree 1 polynomial, and this is a degree 2 polynomial. If I pick this family over a line, like complex numbers, for t not equal to 0, I still see if I set this equal to 0, I'm looking at a cubic curve. Because it's a curve which is a 0 set of a polynomial, homogeneous polynomial degree 3, and that could be an elliptic curve with genus 1. Okay, but when t deforms, changes, I'm looking at a family of these things. When t becomes 0, this thing goes away, and it is still a cubic curve, because it's the 0 locus of a polynomial of degree 3, but it's the 0 locus of the honest product of 2 polynomials, f1 and f2. And we know from algebraic geometry that the 0 locus of this thing is the 0 locus of the first one union 0 locus of the second one, and that's the nodal singularity. So as I follow a path from here to here, maybe this path is the line A1. Maybe in here I'm looking at t not equal to 0, and over here I'm looking at t equal to 0. As I'm deforming this thing, it becomes a normal crossing singularity, and it's still an elliptic curve, so it becomes something like this, but with a node to some other component. P1 to Pn. Okay, so it can also, this can happen to it. And then, okay, but now you can actually see. Why am I drawing this picture? Because the moduli functor is such, the moduli space is such sophisticated object that parameterizes not just those smooth curves, but the way that they become singular is also captured by it by looking at appropriate paths. This is one example of that path. But even more singularities. This is a divisor that parameterizes pictures like this up to deformation. And this is a divisor that understands how I can get a singular curve by squeezing this part. But then these two divisors meet. So there is a codimension 2 thing. By the way, this is not a line and this is not a line. These could have dimension whatever, 127. But the intersection of them is codimension 2. And the codimension 2 locus, which is a smaller locus, is the deeper locus in the sense that it understands deeper type of similarities. So if I start a curve going to here, and if I start with the curve and go to here, and then I follow the path and deform these things further, I will see the mixture of the two possible singularities. So here I see nodal curves, and here I see curves with a squeezed edge like that. And here, on this very locus of intersection of these two-way divisors, I will see pictures like this connected to tori with this. Okay, P1. Yeah. Okay. This thing actually can deform to this thing. And this is exactly what you will see in the intersection of these two divisors. Divisors are where the things can become ugly, and intersection of divisors shows you uglier and uglier things. And that's what the moduli space is. Okay, so these are, by the way, the boundary of the compactification of M bar Gn, and which are the way divisors. That's the picture I wanted to show you for you to kind of understand what this moduli space looks like. Imagine that this picture, I could have drawn this picture like a cube, and I would have the edges, those are the divisors, and then the intersection of edges, things like this, and then intersection of the edges, the vertices, and that's even worse kind of singularity. I can keep going like that. But this is phenomenal because as soon as you work on this space, why do we need a coarse moduli space after all? We discussed this whole thing is motivated by topological string. These are string world sheets, and under deformations of the strings and the ambient space, because of gravitational fluctuations, the curves become singular. Okay, and you would like to count how many are they, and you kind of would like to, after that, calculate energy or free energy of the system of the strings interacting with each other. So it's an integral, right? You cannot integrate over a functor. You need to integrate over a space. This is that space. Okay, but needless to say, we are not doing calculus, and we are not doing differential geometry either, because this space is very ugly looking. So can we have integral defined on it? Or is it something which mimics properties of integration, but it's not really integration? It's a certain algebraic manipulation that produces a number out of this ugly looking space, and that's the content of Gromov-Witten theory and this course. Okay. All right. So this is that. Now examples of moduli of curves and basic constructions. So smooth curves of genus 0. So this is the M0n. I'm not going to put the bar on it because this is the smooth, open, dense interior bulk of this moduli space. This is parameterizing smooth curves. It's the interior of the compactification of M bar 0n, and it is defined for, okay, so 2g minus 2. The theorem tells us that this only non-empty space if 2g minus 2 plus n is bigger than 0. So 2g, this is 0, minus 2 plus n. So this is minus 2 plus n bigger than 0. So that means n needs to be bigger than equal to 3. Right? You're looking at genus 0 curves, and you would like to have a space that parameterizes them with finite automorphisms. This constraint already captures the thing that we discussed last time. To capture this constraint, n needs to be at least 3 special points or 3 mark points. So these are smooth though. So here markings are the only possibilities. I didn't allow here in the interior, I don't allow nodes. So special means here only the markings for the interior. We know that every smooth genus 0 curve C is isomorphic to a P1, right? We discussed that. Thus, beginning with simplest case, n equal to 3, n needs to be at least 3, but simplest case is n equal to 3. Every curve C, P1, P2, P3 is part of M0, 3. Every curve in here is, okay, so I can say a curve in here as a point of M03. I can use straight M03 because this is a space and a point of it makes sense. Or I can write it like that. Or I can say, let me use the second notation, is the realization of M03 at points. So categorical object in here, which is the representation of a point. Okay, and what is that? That's the spectrum of C. There's only one who's the ideal, and that's the point. So I can write it like this too. So this is isomorphic to that thing. Okay. Then, as we discussed, there exists an automorphism of P1, which is an element, semicolon, which is an element of PGL2Z, and we know how PGL2C, how PGL2C acts on the two homogeneous coordinates of P1, sending the three mark points to 0, 1, and infinity. So, because the moduli functors parameterize these things up to automorphism, then I can say that the original curve with three mark points on it, which is genus 0, is isomorphic to P1 with three markings on it, and that is isomorphic to P1 with the canonical three markings on it. There is a map that if you pick the P1, if you pick the sphere, P1 is the sphere, pick 3 points on it, there is a map that deforms this sphere, keeps it as a sphere, isomorphic to the sphere at least. Maybe it becomes like a stretches, don't care, we don't care about that, everything is a scale invariant, but then sends these 3 points on the surface to the 0 and 1 and infinity. So 0 is the north pole, infinity is the, so okay, 0 is the south pole, infinity is the north pole, and 1 is anything on the diagonal, in the diagonal, what is it called? Equator. Yeah. Okay. That's up to isomorphism. There exists a unique smooth genus 0 curve with 3 distinct markings. i.e., the fiber of the moduli functor M03 over the spectrum of C is a point. Okay. Actually, M03 is a point. So, okay, anyway, it's just a point. It's just a P1 with 3 markings on it. And that's the same as P1 with 0, 1, infinity, and that's unique. So here's a proposition. Actually, proposition M03 is a point, which is the spectrum of an algebraically closed field such as complex numbers. This is the abstract point. So whenever in algebraic geometry someone says point, you should think of spectrum of an algebraically closed field. So that's how it is for graduate students. A point is a spectrum of K, algebraically closed field. There is only one ideal in here. Okay. All right. So this is a fine moduli space. Fine moduli space for the functor M03, and together with and comes with universal family. Comes with universal family I, which is P1 over spectrum of C, and P1 is equal to 0, P2 is equal to 1, and P3 is equal to infinity, are maps from the spectrum of C to P1. That's your universal family. Okay, so that's that. That's a theorem. I'm wondering whether I should prove it or not. So, to the experts, the proof of this actually is more non-trivial than you think. We needed to prove a proposition to prove that this is the case. Maybe I can skip the proof of this. No, actually, let's prove it, because this is supposed to be an advanced lecture series for IMSA. So it's not bad if I include this thing. So, but I give a rough sketch of the proof. In order to prove the proposition, we need to prove the following. Is this the following lemma? I'm not going to prove this lemma, but I tell you proving which lemma helps you with it. Okay, it's a lemma as follows. So lemma, you need to first prove that let pi from C to B be a smooth, proper, because I know that there are also algebraic geometers and experts in the audience who are logged in via Zoom. So I better think that probably we should include the proof. So let pi from C to B be a smooth, proper surjective, locally finitely presented morphism of relative dimension over complex numbers 1. So it's a parametrizing family of curves over some base B. I called it B because it's the base. Relative dimension, it could also be less than or equal to 1. So it could be zero dimensional also, with geometric fibers isomorphic to P1. So let's say I have a family of P1s over some base. This lemma says the following. Certain things you can prove about this family. Whenever you give me a family of P1s over some base, where the morphism is locally finitely presented, smooth, proper, and surjective, okay, you can prove the following things about it. 1, A, if I admits one section, that means any section, I think people in algebraic geometry, if any in the Zoom, they would very much recognize this theorem. If it admits one section, then one can find a rank 2 vector bundle on this base B. We call it vector bundle E, such that such that C is isomorphic to a projective bundle. So C is the projectivization of this vector bundle E over B. As soon as you have one section, allows you to realize C, the total space of the family, as a projectivization of rank 2 bundle. Oh, good, whatever. Why are we interested in this? You will see. Let me tell you why we are interested in this. M03 over base is giving you families of P1 with 3 markings. But remember that when I said we are looking at family markings or sections. So now I'm proving some statements about sections. Let's say I have a family of P1s over some base. If I have one section, there's something you can tell about the family. Then I'm going to say if I have 2 sections, there's something further you can say about it. But if I have 3 sections, I can also say something about it. And the third one is the one we're going to use. Okay. All right, so if I have 2 sections, if pi admits 2 sections, P1 and P2 from B to C, then E, the vector bundle E, splits. Actually, you can show that it splits as a direct sum. Splits as a direct sum. So E becomes isomorphic to sum of 2 line bundles, L1 and L2 of line bundles. Line bundles are C if pi admits 3 sections, P1, P2, P3, disjoint sections, okay, from B to C, then we take E as, we define it as trivial length rank 2 bundles. So if it admits 3 sections, it at least admits 2 sections. So it's the direct sum of 2 line bundles. But the third one can actually show you that you can take that rank 2 split bundle as O plus O, trivial bundle, above, so that C is isomorphic to trivial projective bundle. Okay, so this C, if it admits 1 section at least, C is the projectivization of a rank 2 bundle. If it admits 2 sections, this rank 2 bundle is a split. So it's the projectivization of L1 plus L2. But if it admits 3 sections, this split rank 2 bundle is O plus O, and C will be projectivization of, which notation did I use? P. Projectivization of O plus O, and the gives you the projective, trivial projective bundle, and that's isomorphic actually to B times P1. You see, this is a fact that you can actually see in algebraic geometry books. This, you know what this is. This is trivial fibration. Fibration, total space of a fibration is dimension, whatever dimension of B plus dimension of the fiber. It becomes this thing if the bundle from which you get that fibration is trivial. So these 2 things are compatible with each other, right? This is what the trivial fibration is. Okay, so this is a statement about having a family of P1s over a base. M03 is a family of 3 P1s over a base whenever I pick a base of that family. And it has 3 sections. It admits 3 sections. So I'm going to use it. I'm going to use this statement. Okay. So proof of proposition about M03. Okay, now we are going to use that lemma. By definition, we need to show that M03 is isomorphic to a point. So I'm going to call this thing so M over S, which is a category of schemes for some complex numbers, S to a point. The functor sends the element of the category to set. And this set is going to be a point. And this point is the spectrum of C, or spectrum of algebraically closed. So that we want to show by definition. This means that we need to show that any family of smooth genus 0 curves, I from C to S together with sections, 3 sections, I P1, P2, P3 from S to C, which is an element of M03 over S, is isomorphic to the trivial family, to the trivial family. What is that? Which is S. So I would like have pi S times P1 goes to S together with 0, 1, infinity, which is from S to S times P1. In order to show that your whole space for any choice of parameterizing the scheme you pick is a point, you need to show that all possible families you get this way are the trivial family. But the trivial family by construction has a meaning. It means that total space of this family, this is what a trivial family over S is. It's a family of P1s. A trivial family of P1s is S times P1. But you see, it's almost immediate from that statement, right? That's a trivial family of curves with 3 markings over base B. It's the projectization of O plus O, and it is P times P1. Now your family is going to be S times P1. So after you prove this lemma, it's immediately implied. Okay? So it's the trivial family. By earlier lemma, the 3 sections P1, P2, P3 from S to S times P1 are assumed to be disjoint. And induce a map P1, P2, P3 from S to 3 copies of P1 cubed minus the big diagonal big diagonal. Okay. Then an automorphism. S times P1, S times P1, sending P1, P2, P3 to 0, 1, infinity, 0, 1, infinity, is given by S times P1 to S times P1, which sends S, a point of S and a point of P1, S comma P, so a point of P1 and a point of S to point of S and so let me call this thing something A. I'm going to call this map A. So A acting on S inverse times P. This gives the desired isomorphism of the families. So by the fact that your family has 3 distinguished smooth points as sections, and it's a family of P1s, we use that lemma. We realize based on that, total space of this family is a projectivization of a split rank 2 bundle, which besides that is also O plus O. It's a trivial projective fibration. And that gives you the trivial fibration. The trivial fibration is S times P1. And once you have that, I need to tell you what are the automorphisms and what the moduli space would uniquely be parameterizing then. So we know that as soon as you give me 3 sections, this is something we studied last time. It always sends you to 3 copies of P1 because I can move these sections around. They're distinct, so you're outside of the big diagonal. And so then an automorphism is basically a morphism between these 2 trivial families, and we are telling you uniquely what that thing is. So it's just one point. No matter what your parameterizing scheme is, it's always going to be a unique point. So M03 is a point, no matter what. So M03 is always realization of the functor at a point. So M03 is a point. A priori, M03 is the underlying cross moduli space of the moduli functor parameterized over any choice of schemes, but it doesn't matter. These are trivial families and they are all isomorphic to each other. So it doesn't matter whether I put S or a T or a spec of C, it's going to be all the same. So it's a point. Okay, so that's it. I think that's for M03. I think this is a good place to stop today. And then I will tell you, now that we know M03 is a point, I will show you what M04 is, and that's beautiful. As soon as you know M03 is a point, M04 is very understandable. Then M0n is very understandable, basically. And you suddenly, you feel like I understand all the, for all n, genus zero, parameterization of genus zero curves. So that's where we continue. Thank you.